To start Unit 9, and in Section 9.1, we're going to identify and define terms of a circle. So as a warm-up today, I just want you to take a second and pause this video and just think of some vocabulary words that you know that are associated with a circle. So you've learned lots of things about circles, and some of which we're going to go over today, but maybe just pause and go through a few things that you feel like you know. So let's go down below the warm-up and start with what is a circle. So it says by definition, a circle is a set of all points equidistant. Which we should know equi means like the same. So we're talking about the same distance. So a circle is a set of all points that are the same distance from a given point, which is called the center. So if I start with a point, would be the center of my circle, and I found a length out to a point. And if I copied that same length from the center in all different directions, I start to create a pattern of the same distance, that equidistance from the center of a circle. Now, if I was really good at drawing, that would have turned out a little bit better. And when we connect all those, we end up with a circle. So again, that circle is a set of all points from that center that are equidistant. And hopefully we know this next term, but what we've just really created was a whole bunch of radii. So a radius, so plural would be radii. A radius is any segment with endpoints that are the center, so the center of that circle, and a point on the circle. So I've got a nicer one drawn that I just drew above. So on a circle, if we had a center A, and going out to any point on the circle, maybe it's called B, we have a radius. This is a segment. So if you were asked to name a radius, we would want to say something like AB, segment AB. Or remember, those letters can be reversed. So remember, the plural of this is radii. So radii is spelled with two I's. That would be our plural form of radius. All right, the next one maybe is a little bit newer. A segment with endpoints on the circle is called a chord. So if we talk about a segment, we know that that has ending points. It doesn't go on forever. So if the ending points of a segment are on the circle, then we call that a chord. So a chord could look something like this segment DE or ED. It just has to touch the circle in 2 points, and it's a segment. A diameter, which is one hopefully we know, is any chord. So we have that new definition. A diameter is any chord with endpoints that are on the circle, and here's the bigger piece, it passes through the center of our circle. So a diameter is a chord, it just has to pass through the center. And if it does, then the diameter has to be the longest chord of a circle. So a chord in this picture here is also a diameter. So the question can be asked, is a chord always a diameter? And the answer to that would be no. And we've got a picture of that from above. This is a chord, but it's not a diameter. But if I ask that backwards, is a diameter always a chord? That would be yes. That would be always is going to be true. All right, let's talk about some angles. It says an angle that intersects a circle in 2 points and that has its vertex at the center of a circle is called a central angle. So let's look at this picture here. So we have to have a center of our circle, and an angle we know consists of 2 sides. So here we have 2 sides. And if the vertex of that angle is the center, we call this angle the central angle. And if we were labeling this with our notation, we have our angle marking. And remember that angle vertex has to be the third or the middle of those 3 letters. Or we could go backwards. As long as that vertex is in the middle, that's what matters. So if our vertex is at the center of a circle, we call this a central angle. Well, not all vertices have to be at the center. So our next definition says an angle that intersects a circle in 2 points and has its vertex on the circle. If this happens, we call this an inscribed angle. So our picture, we still have two sides of an angle, but this time our vertex, which would be B, is actually on the circle. So we call this an inscribed angle. So again, if I wanted to label this, I could call it DBC. So again, we just want that vertex to be in the middle, or we could go backwards, CBD. The next one we talk about is what's called circumscribed. So we say a polygon, which we know a polygon has to have sides. Squares, rectangles, triangles, pentagons, all of those have sides. So a polygon that is circumscribed by a circle. This means it has all of its vertices on the circle, and the polygon's interior is completely contained within the circle. So I've got this statement here to think about this and our picture that's next to it. So when we're talking about circumscribed, we can say circle A, so our center, circle A, is circumscribed about. So we've got a circle that's circumscribed about quadrilateral BCDE. So to be circumscribed means that all of the vertices have to be on the circle, and this whole shape, this whole quadrilateral, has to be inside of the circle. Well, we have kind of the opposite of that. It says a planar shape or solid completely enclosed by or fits snugly inside another geometric figure or solid is called an inscribed figure. So again, I've got a statement to kind of help us think about this one. Quadrilateral BCDE, so we're starting with the shape this time, is inscribed in circle A. So we say it's inscribed in circle A if it completely is enclosed inside, fits snugly to this circle. So we say a circle is circumscribed about a shape, or we can say a shape is inscribed inside of a circle. So they can end up with the exact same picture, but just the direction you're talking about it is a little different. Okay, these next couple of definitions are going to make us think about trigonometry because we just finished that unit. And there is a little bit of a relationship about these words and the trig words that we just were talking about, but we're not going to go into that relationship this year. So just kind of know in the back of your head, yes, there is one, but you'll get to that in a later class. So in a circle, if a line intersects a circle in only one point, we call this a tangent line. So if I look at my picture here, I've got a circle A and I've got a line that's outside of my circle, and I'm noticing it only touches my circle right here at B. We would call this whole line, this is a tangent line. So I'm just going to go ahead and label that. That line is a tangent line. And to be a little more specific about that point, it says the point where the tangent line and the circle intersect is called the point of tangency. So for this picture, that would be this point B. This is our point of tangency. So a tangent line only touches a circle in one point, at one point, and that point is called the point of tangency. We also have what's called a secant line, which we did briefly talk about in secondary 1. So yes, this should sound a little familiar. But with a circle, a line that intersects a circle in 2 points is called a secant line. So when I look again at my circle, this line is going through my circle and intersecting at a C and a B. So this line BC, we would say, is a secant line to this circle A. So tangent should only touch a circle at one point, that point of tangency, where a secant line should go through twice. So let's practice our vocabulary. Let's go ahead and turn the page. Example 1 says to identify a chord, a tangent line, a diameter, 2 radii, remember that's plural for radius, the center, a point of tangency, and a central angle. So just practicing our notations. So we've kind of got a lot going on in this picture. And let's start with A. A says a chord. Now remember, a chord by definition just needs to touch a circle in 2 points. So it could be a diameter and it could not be a diameter. So the first one I kind of noticing is there's this chord BD. So segment BD is touching our circle in 2 points and it's on the inside of our circle. I also notice that there's a diameter here, which is CG, and a diameter is also a chord. And I'm going to go ahead and put that down on problem C because that's asking me for the diameter. This next one sometimes gets missed because there's a line drawn through it. So I'm looking at this line JF, and yes, this is a line, but if I only look from J to F, I can see just a segment. So that is also considered a chord. If I just look at that segment from J to F, that is a chord. A tangent line, one of our newer words, a tangent line has to only intersect a circle once. So I'm kind of noticing this intersection at G and this line HG that goes through it. So a tangent line is a line. So I would like to call this with 2 letters, it doesn't matter which one comes first, and put my line marking above that. A radius. A radius has to go from the center to a point on the circle. And my circle starts at A. So a radius would have to come from A, and it looks like I can go from A to G, A to E, and A to C. So in this problem, there are 3 different radii, AG, AE, and AC. So 3 different radii that have been drawn in there. Point of tangency, I guess technically we could have done that one back at B because we had a tangent line, which means the point of tangency is where that line touched the circle. So that should be at problem or point G. Center, this should be the easiest one. A center of our circle in this case is A. I've already used that to help me find some other things. And then last one, a central angle. Now a central angle has to have its vertex at the center, and that's kind of how I'm going to remember that, central and center. So when I look at this, my vertex is going to have to be at A, and I need 2 sides. So I could have an angle from C to A to E, or from E to A to G. That would work. I could also have, let's see, G, A, E. Oh, what if I had G, A, C? So that whole thing, that whole angle is like side of my circle. So that would be like a 180-degree angle. So that one's one that we can also include. So I'm going to put all of these down. I'm going to start with CAE. And then I'm going to go to GAE. And then I'm going to do that straight angle, GAC. And for all of these angles that I'm labeling, as long as A is in the middle, those first and last letter can go in any direction. All right, let's look at example 2. Identify the term that best describes, and notice that's bolded and underlined, because sometimes you may feel like they fall into 2 categories. So which one best describes the given line, segment, or point? So problem A is got a segment marking above it, so segment AF. So I look and find A and F. I think the best description here would have to be a diameter because it goes through the center. Technically, it is a chord, but more specifically, it's a diameter because it does go through that center. So my best description here would be a diameter. Problem B kind of goes across here. Problem B, segment PF. So from P, which is the center, to F, this is not going all the way across. It's just from the center to a point. So this would definitely be a radius. Problem C is point C. So I find point C outside here on my circle, and that's associated with that line that's tangent to that circle. So that point C must be a point of tangency. Anytime a circle and a line intersect at one point, that point is a point of tangency. Problem D, I notice it's got a line BD. So line BD, what we were just working with, that would have to be a tangent line. It was tangent at that point C. Segment EG, so from E to G, this is going in two places across my circle. It's not a diameter because it doesn't go through the center. So this one just needs to be a chord. PC, from P, that center, to a point on the circle, there's another radius. Line CE, so from C to E, but we're talking about that whole line. So if I was just looking from C to E, that would be a diameter. But I'm looking at the whole line. So a line that crosses a circle twice is called a secant line. And the last one, H, is point P. And point P is just the center of our circle that we've been using already. So all circles, and maybe this is a statement you've already heard before, but all circles are actually similar. All of their, any shapes that we draw inside of them have to be similar. So we're going to prove, it says we're going to prove that all circles are similar. So to prove all circles are similar, you need to prove that their corresponding parts are proportional, which we've done that already several times in other settings. So here is a proof, and it's not a two-column proof. This is called a paragraph proof. Here's a proof that's showing that all circles are similar. So we've kind of given some names and letters to things to kind of help organize this. So it says that we're given angle A is congruent to angle D. So it would be an angle inside this triangle, the center of our circle. We don't know what they are, but they're equal. The radius of circle A is X, and we know any distance from A is going to be X. So we've got two values of X there. And the radius for circle D is Y. So again, we've got two radii there. So both of those are Y. So we're going to prove that circle A is similar to circle D. So I'm going to go through this kind of quickly. You'll probably want some time to kind of think about it and digest it. And if you have some questions about it, you can definitely ask me later. So to start us off with, and maybe some of you already noticed, that we have some isosceles triangles. So AB is congruent to AC, because our triangle here would have to be isosceles if our two radii were exactly the same. And therefore, because we know things about isosceles triangles, angle B has to be the same as angle C. Those are base angles. The same can be said for our smaller triangle. DE and DF are congruent, which means angle E and angle F are congruent. So it says the sum of the angles in a triangle is 180 degrees, which we know. So looking at that big triangle, angle A, B, and C add up to 180. And in our smaller triangle, same. D, E, and F add to 180. And because we know that angle B and C are congruent and E and F are congruent, then we're going to shorten these equations a little bit. So in my first equation, I had A plus B plus C. But B and C are the exact same. So I'm just going to give it one name. I'm going to say we have two angle B's. I could put two angle C's there because they're the same, but I put two angle B. And similar can be done in our smaller triangle. E and F are the same, so I'm just going to say we have two of angle E, and together still they add to 180. So if we solve each of these equations for the angle A and the angle D, we're going to get, and I've got it typed here, that angle A is 180 minus 2 times angle B, so we would just subtract that over. Same for angle D, we would just subtract over 2 times angle E. And since we know angle A and angle D are congruent because they were both given to us as central angles there, then we can take each of their equations and set them equal. So I can substitute out for angle A and put in and same with angle D, and put in what they're equal to. And because we know angle, so by angle similarity, we now have that these two triangles are similar. So because they're similar, I'm just going to highlight that. We have a whole bunch of proportions that we can now set up. And this is really the focus of what we're going to be taking from this. Because these triangles are similar, then all these proportions can come out. So we're going to start with the proportion of their radii. So if I take the radius from our first triangle, I'll call it AB first, and a radius from my second triangle, so DE, that circle, excuse me. We're just going to use X over Y as they were labeled in the picture. And the ratio of the radii of the circle is now going to be considered X over Y. The diameter, we know the diameter has to go all the way across the circle. So in my big circle, if one radii is X, another radii that would continue to our diameter would be another X. So the diameter of our circle is going to be 2X, and for our other circle, it would have to be 2Y. So we can set up a ratio of the diameters. So a ratio of the diameters of our circle would be 2X over 2Y, which we can simplify by dividing by 2, and we end up with that same ratio of XY, those radii compared to each other. Circumference, it's maybe been a while since you've done circumference, but circumference of a circle is 2 pi times the radius. So in circle A, our radius is X, so that's why it says 2 pi X. And for our circle D, our radius is Y, so 2 pi Y. So when we look at the radius, or the circumference, for the big circle compared to the small circle, the 2 pi's will divide out, again leaving us with this ratio of our radii, X compared to Y. So when circles are similar, we can make a ratio of their radii, their diameter, their circumference, and all of them should simplify to the same X over Y. So let's look at one problem that will be similar to what you'll see on your assignment. So if we're given a circle, and we don't even have to have pictures, but if we're given a circle with a radius of 3 and another circle with a radius of 5, it wants us to compare the ratios, so we're going to be writing some ratios, of the 2 radii, the 2 diameters, and the 2 circumferences. So you'll want to make sure you label so I know which one is which, because technically they're all going to end up to be the same. So let's just start with radii. Well, it said that our radii of our first circle was 3 and our second circle was 5. Now, it didn't tell me which one had to be in the numerator and which one has to be in the denominator. So if you choose to compare it as 3 to 5, that would be great. If you decide to do it 5 compared to 3, that would also be great. So you could have the reciprocal of what I have. Diameter, we know diameter is 2 times the radius. So I would be taking 2 times my first radius, or you could just call that 6, and 2 times my second diameter or radius, or you could just call that 10. So if I multiplied those together, I would definitely want to simplify. And when I simplify, I should see that same radius that I saw when I did, ratio when I did my radius ratio. And then we have circumference. Circumference is 2 pi times the radius. So for my smaller circle, 2 pi times 3. And then for my bigger circle, 2 pi times 5. So I could multiply these together, but this time I'm not going to, because I see that those 2 pi's divide out, and they leave me with the same ratio of 3 to 5. So again, if you chose to do 5 over 3 to start, all of your ratios should end up to be 5 over 3. So our ratios, when we have similar circles, end up to be the exact same ratio. I do want to see how you set up the ratio and that it's simplified, in this case, to 3/5. Same with your circumference. Set it up and let me see that you simplified it to give you the same ratio. All right, go ahead and self-assess, and good luck on your assignment.